Welcome to the second lecture on nonlinear control systems. In this lecture, we'll be talking about common nonlinear system behavior. Okay, so before we discuss how nonlinear systems behave fundamentally, we have to discuss a concept called the concept of equilibrium point. So this equilibrium point you will basically understand if you remember from your physics classes that you used to study something called the equilibrium position of objects. So if you have, say, for example, something like a cone, and you place it like this on a surface, if you disturb this cone from this position to the left or to the right, and if the displacement is small, then the cone will come back to this position. And if this cone is actually in some position which is not at this, it's like this, it will go to this position. After maybe wobbling a little bit around this position, it will come back to this position and settle down there. So you used to call this position the equilibrium position, and you used to say that this is a stable equilibrium. It's a stable equilibrium position because the cone if disturbed from this position slightly is going to come back and settle down at this position, stabilize at this position. So basically the concept of equilibrium point is actually similar. It means that if your system reaches x, some point in the state space x, it stays at x. So a point is called the equilibrium point. Roughly, a point x would be called an equilibrium point, right? So let me write this: a point x in the state space for a system is called an equilibrium point. Equilibrium point if the system upon reaching x stays at x if undisturbed, right? So you're making the inputs 0. Now what is the general form? How would you write a nonlinear system, right? Or a general system in the state space form. You write this in like you used to write linear systems, like x dot is equal to ax plus bu, where x was an n-dimensional vector and u were the inputs, y is equal to cx. A more general way of writing a system, and that's how you would write nonlinear systems, would be x dot is equal to f x comma u, where f is some nonlinear function of x and u, right? So this is also not very general, but a more general notation would be f x dot comma x comma u is equal to 0, right? In both these notations, x belongs to the n-dimensional space and u is the number of inputs, so it belongs to, say, a p-dimensional space. So these are both notations for general notations for dynamical systems, but this notation is called the explicit notation, and this is the implicit notation, right? So we'll be concentrating on this notation because for our purpose this notation is sufficient. So a nonlinear system in general would be something like x dot is equal to f x comma u. right? Where X belongs to Rn, and F is actually a mapping. U belongs to Rp, and F is actually a mapping from the domain, which is Rn plus P. That means it takes X, n inputs from X, P inputs from U, and then this mapping goes to Rn, because this is X dot is an n-dimensional vector, right? So this was just a small just to give you some idea about the notation. We are actually discussing the equilibrium point. So what I've said is that if a system reaches X, it stays at X. That's the equilibrium point. So if it reaches X, stays at X, right? And let us initially talk about systems that don't respond to inputs, that are homogeneous. So we're talking about systems of this form: X dot is equal to Fx, right? Please remember that this is not a single equation, it's a series of equations, right? So it'll be a series of equations. So it's going to be something like x1 is equal to f x1 comma x2 comma xn, right? X2 is f1, it will be some f2 x1 comma x2 comma xn, right? And this will go all the way up to xn, which will be fn x1 comma x2 comma xn. So this is the actual nonlinear system of n dimensions, and this is a compact way of representing it. So internally there are there is a possibility that there would be n nonlinear functions, and all of them would be functions of n variables. So the equilibrium point is when the system reaches X, it stays at X. That means basically that there is no change in X. That means the state velocity vector is 0. So this is the definition of equilibrium point. The state velocity should be 0 at the equilibrium point. And there are two types, as we have just seen. For this cone that we placed here, the velocity became 0 at this point after some time, after it had been initially disturbed. And if we take the same cone and balance it like this with the top pointing downwards, then there is a possibility that this cone is going to stay at this point, at this position also, but this would be an unstable equilibrium point. Because unstable equilibrium position, because if it is disturbed from this position, it is not going to come back to this position again. So you have this concept of an equilibrium point where the state velocity becomes 0, which means that the system stabilizes, it remains at that position. And then you have this difference between a stable equilibrium point and an unstable equilibrium point, wherein the system, if disturbed from a stable equilibrium point, stays at the point, and the system, if disturbed from an unstable equilibrium point, does not come back to the unstable equilibrium point. It moves away from it. And we have just seen that the fundamental definition of the equilibrium point is mathematically the state velocity at the equilibrium point would be equal to 0. And for a nonlinear system, which is given by x dot is equal to fx, this translates into this equation, that fx equal to 0. Okay. Now all this we have seen just to understand how a nonlinear system is going to behave in general. So what are the characteristics of a nonlinear system, and how does it differentiate from a linear system? So let us try to make a comparison in tabular form. Suppose I put my linear system behavior here on the left hand side, right, and my nonlinear system here on the right hand side, right. And let me try to see how a linear system compares with reference to a nonlinear system in order to understand nonlinear system behavior. So you have seen one big definition, that is, in case of a linear time invariant system, you'll write x dot is equal to ax plus bu, y is equal to cx here. But for a nonlinear system, this equation would change. It's going to become x dot is equal to fx comma u, and y can be a function, again a nonlinear function of x, so it would be or for our case, let us take it to be an algebraic combination of the state vectors, so we can take it to be cx, but in general this may also not be true. And the this is how we write it in general. These are both explicit notations, as I've told you. If you have an autonomous system in which you don't have the u term, you'll write x dot is equal to ax, and for the nonlinear system you'll write x dot is equal to fx, right? So this is as far as the notation is concerned. And what about equilibrium points? So x dot is equal to ax has one equilibrium point. What is the equilibrium point? Equilibrium point would be given by x dot equal to 0, which implies that x is equal to 0 for non-singular A. So the linear system has one equilibrium point, and that equilibrium point is given by x is equal to 0 for non-singular A, right? And this is not necessarily true for a nonlinear system, right? A nonlinear system, the equilibrium point is again x dot equal to 0, which will be given by fx equal to 0, and this equation fx is equal to 0 may not give you one equilibrium point, right? Like for example, if my nonlinear system is something like x dot is equal to minus x plus x square, it's a one-dimensional system, so x belongs to R. So my x dot is equal to 0 implies minus x plus x square equal to 0. So this implies x into 1 minus x equal to 0, which implies x is equal to 0 comma 1. So the nonlinear system here has two equilibrium points, x is equal to 0 and x is equal to 1, right? So in nonlinear system, this one big difference between a nonlinear system and a linear system with non-singular A is that you can have multiple equilibrium points for nonlinear systems. Right? So that is why the notion of stability changes for nonlinear systems. Right? What is how do you basically understand stability with reference to linear systems? So stability for linear systems the equilibrium point is stable if all eigenvalues of A have negative real parts. We have already seen this. And we don't say that in linear systems that the equilibrium point is stable or unstable. We say a linear system is stable or unstable, right? So we talk about stability of systems. We don't talk about stability of equilibrium points in general when you talk about linear systems. Why? Because there is only one equilibrium point. So when there is only one equilibrium point, it means that when we say that the system is stable, it automatically means that the equilibrium point is stable. But for nonlinear systems, right, see, you have to talk about the stability of the multiple equilibrium points. So the notion of stability changes. What is the notion? Instead of talking about whether the system is stable or unstable, instead of saying whether the system is stable or unstable, you talk about whether the equilibrium point is stable or unstable for a nonlinear system. And why is that? It is because a nonlinear system may have multiple equilibrium points, as we have already seen, and in addition to having multiple equilibrium points, some of the equilibrium points might be stable and some equilibrium points might be unstable, right? So a simple example of something like this could be, say a bowl and a bowl and a ball example. In this case, the ball would finally stabilize at this position, at this mean position. So this is a stable equilibrium point, stable equilibrium position. If you invert this bowl, you can stabilize this ball here, but this is an unstable equilibrium position. And if you have a structure like, say for example this, then this structure has two, in this structure the ball has two equilibrium positions. This first in equilibrium position is stable and the second equilibrium position is unstable. So the same system, the ball and the structure system, has two equilibrium positions. One is stable and one is unstable. So the first important thing as far as stability is concerned, we talk about stability of equilibrium points in nonlinear systems. So we will not talk about stability of the nonlinear system, we will talk about stability of the equilibrium point of the nonlinear system. And the other important distinction as far as stability is concerned is that the stability of non-linear systems may depend on initial conditions, may depend on initial conditions, right? And why is that? Say for example, in this example only, this is something that is going down, right? It has no end for 2 minutes, and if our ball starts from here, then it is going to stabilize. So this initial condition is that the ball is starting from here, it is going to stabilize around this equilibrium position. But if a ball starts from here and it goes down the hill, then it has no chance of coming back. Or you can try to understand it like the displacement of ball is continuously increasing with time, the system has become unstable. So this initial condition here is when the ball is here, and the ball starts from here, the system remains stable. And if the ball starts from this point and it goes down the hill like this, then the system is unstable. So the stability is dependent upon initial conditions, and this is never the case for linear systems, right? So this is very important to understand this second distinction as far as stability is concerned. The third important thing is that you have a concept of in linear systems, you have a concept of Bibo stability, right? So what is Bibo stability? Bibo stability is stability, it's Bibo stability, right? Bounded input, bounded output stability, right? So this is stability with reference to inputs, and you say the system has a bounded output whenever the input is bounded, right? It's not the more general definition of stability, but it's a particular class. It's a particular class of stability in which you say that the system output is supposed to remain bounded for bounded inputs, right? And this stability in general, when you talk about negative eigenvalues, is called asymptotic stability. So if a system has, for linear system, if the eigenvalues are negative, it implies that the system is asymptotically stable, right? So this is a more general understanding of stability, asymptotic stability. Now, Bibos, if a system is asymptotically stable, it automatically implies that it is Bibo stable. So a linear system, when it is asymptotically stable, implies that it is Bibo stable. But this is not necessarily true for nonlinear systems, right? So in nonlinear systems, asymptotic stability may not imply Bibo stability, right? So this is another important thing. Even in fact, an example would be something like x dot is equal to, say for example, x into u, right? So suppose you have a system like this, and this x, it would converge to 0 if u is -1, if it is negative, but it will not converge to 0 if u is not -1, if it is not negative, right? It otherwise it will extend to infinity. So despite the fact that u is equal to +1, for example, is a bounded input, right? The system does not remain stable for this input. So the concept of stability for nonlinear systems is input dependent as well, right? Now, another important understanding of stability with respect to nonlinear inputs is another important feature, distinguishing feature between linear and nonlinear systems would be, if you talk about the transient response of a nonlinear system, right? So the transient response of a linear system is composed of the natural modes of the system and can be obtained analytically, right? Right. This is another characteristic feature of linear systems which is not present in nonlinear systems, right? And another important thing is that for linear systems, when you do sinusoidal steady state analysis, you know that a sinusoidal input leads to a sinusoidal output of the same frequency for linear systems, right? And all are, in electrical engineering, all our AC sinusoidal steady state analysis, whether it be for power systems, for machines, is based on this principle, because the underlying systems are treated as linear. So a sinusoidal input leads to a sinusoidal output of the same frequency, and because of this property you're able to draw phasor diagrams and other things, right? But this property is again not present in nonlinear systems, right? So this was about stability and a little bit idea about input output response and the difference between a linear system and a nonlinear system. Now let us come to some other peculiar behavior of nonlinear system. There is a behavior of nonlinear system, a particular characteristic feature of nonlinear system, which is called a limit cycle, right? So limit cycle, this is something that is not present in linear systems. What is this limit cycle? Nonlinear systems will display oscillations, some of them. Nonlinear systems can, right? So not all, but some of them can display oscillations of fixed amplitude and fixed period, right? Fixed time period without external excitation, without external excitation, right? And these oscillations are called limit cycles, right? These oscillations are called limit cycles, and they are also called self-excited oscillations. So this is very peculiar, right? What it means is that a nonlinear system would oscillate. Its variables basically would show oscillatory behavior, and they'll be sustained, and they'll be without external excitation, right? You also have oscillations in linear systems, wherein if you remember, for marginally stable systems which have poles exactly on the y-axis, you have a marginally stable behavior like this, right? You have sustained oscillations for linear systems as well, but the difference is that these oscillations are uh, are not of a fixed amplitude and a fixed amplitude, at least, right? And the other important thing is that these oscillations are very sensitive to changes in system parameters. So for a marginally stable system, you may have sustained oscillations, but these oscillations would be very sensitive, to parameter variations, right? So a slight difference in the parameters would bring these poles to the left or take them to the right, and then these oscillations would either die out or they'll become they'll increase with time. The system becomes unstable, right? But the limit cycle for a nonlinear system is such an oscillation that the oscillations are not sensitive, not really sensitive to parameter variations, and these oscillations are also independent of initial conditions. So these oscillations are not sensitive to parameter variations, and these oscillations are independent of initial conditions, right? So our system is finally going to settle down into an oscillatory behavior. An example of this system is something which is called a van der Pol oscillator. Van der Pol oscillator. Mx double dot plus 2c x square minus 1 x dot plus kx equal to 0. This is a nonlinear system of equations in which, if you see the behavior of so this is a nonlinear equation, not a system, sorry. So if you see the behavior of xt with respect to time, right, you'll see that finally what happens is that the system will settle down irrespective of the initial conditions. So you start from here or you start from here, right? Your system is finally going to settle down at a similar kind of sustained oscillatory behavior at the end, right? They're not write very well, so it's like if you start from some other initial condition, right? Let me erase this one first. So like if you start from some other initial condition, although in the beginning the behavior would be different, but finally the oscillatory behavior would be similar, right? So an example is the van der Pol oscillator. So this is a very peculiar phenomena to nonlinear systems. Two other things which are peculiar to nonlinear systems are called bifurcations and chaos. Bifurcation is defined as quantitative change of parameters leading to qualitative change in system properties. So quantitative change of system parameters leading to big qualitative change in system properties, right? So like you can even think of like the number of some parameters are changing, so the number of equilibrium points is changing, their stability is changing, and many things are changing. Normally, if some parameters are changed slightly in linear systems, you will not see a very big change as far as the properties are concerned. But for nonlinear systems, bifurcations implies that a slight change or some changes in system parameters leads to big changes in qualitative changes in system properties, changes in the number of equilibrium points or changes in the stability of the equilibrium points. Chaos is another important characteristic of nonlinear systems, and what this implies is that system output is extremely sensitive to initial conditions, right? It's basically the unpredictability of the system output, right? This is opposed to linear systems, because in linear systems a small change in initial conditions can cause a small difference in output. But for nonlinear systems, a small change in initial conditions can cause a big change in the output, right? And your system essentially becomes unpredictable, because you don't know the initial conditions so exactly. So this is only present in systems which are nonlinear, and basically chaos is present in strongly nonlinear systems, right? So this is the end of this lecture. To sum it up, we have seen a number of things today. We saw the concept of equilibrium point, right? We saw that the equilibrium point is the point where the state velocity becomes zero. And then we also saw the notation for nonlinear systems. And a nonlinear system is, in general, the notation that we're going to look at is x dot is equal to fx comma u. This is not a general notation, but it is fine for our purpose, right? And then we tried to distinguish between linear and nonlinear system properties. The first distinction was that the nonlinear system has multiple equilibrium points, right? And these equilibrium points, being multiple, can be stable, can be unstable. So the notion of stability becomes completely different. We talk about stability of equilibrium points for nonlinear systems, and then the stability is also dependent on initial conditions. It may also be dependent on input. So your system would be input for some would be stable for some inputs, would not be stable for some inputs, right? And then very important properties of nonlinear systems, where linear systems, where we could see the transient response of a linear system and decompose it, right, and get it analytically, is not present in nonlinear system. And the sinusoidal input of a linear system gives the output of sinusoidal of the same frequency in steady state. This property is also not present in nonlinear system. And then we saw three important peculiar properties of nonlinear systems: limit cycle, self-sustained oscillations, without external excitation, which are not sensitive to parameter variations and independent of initial conditions, and similarly bifurcations and chaos. Thanks a lot for listening.